When NASA's New Horizons spacecraft swept past Pluto in 2015, it transformed a dim speck of light into a tangible world. For decades, Pluto had been little more than a mystery, a blurry dot on the edge of the solar system. Yet when New Horizons transmitted its first images back to Earth, it revealed a place far stranger and more dynamic than anyone had imagined. This distant dwarf planet, once dismissed as a frozen relic drifting in darkness, was alive with geological activity. Vast glaciers of nitrogen sprawled across its plains. Towering mountains of solid water ice rose like sentinels from a frozen sea. And above it all shimmered a delicate bluish haze, an atmosphere faintly glowing in the weak sunlight of a faraway star. For scientists, the sight was breathtaking, but it also carried a troubling puzzle. Pluto's atmosphere, though thin and fragile, was much colder than it should have been. According to established models, gases like nitrogen and methane should have absorbed enough sunlight to keep the upper atmosphere around 100 Kelvin, roughly minus 173 degrees Celsius. Yet the readings from New Horizons showed a temperature nearly 30 degrees colder. Something was cooling Pluto's skies far more efficiently than expected, but no one knew what. Theories piled up, calculations were revised, and simulations were refined, but nothing quite fit the data. Then, in 2017, a bold new idea began to circulate, one so strange that many found it hard to believe. There was no way to test it at the time, but that changed when the James Webb Space Telescope, Webb for short, opened its infrared eyes to the universe. To understand why Pluto's atmosphere became such a mystery, it helps to look back at the long road that led to New Horizons. For much of the 20th century, Pluto existed in the public imagination as a lonely outpost 5 billion kilometers from the Sun. It was smaller than Earth's moon, coated in ice, and, many assumed, utterly lifeless. Astronomers could barely make out its color, let alone its surface. Some speculated that Pluto had a tenuous atmosphere that might freeze solid as it drifted farther from the Sun in its long elliptical orbit. But without direct observation, these were little more than educated guesses. That uncertainty made the New Horizons mission urgent. By the early 2000s, scientists realized that if a spacecraft didn't reach Pluto before the mid-2010s, its atmosphere might collapse as temperatures dropped. The window to study a living Pluto would close, perhaps for centuries. So in January 2006, NASA launched New Horizons, sending it on a 9-year voyage across the solar system. When it finally arrived in July 2015, the world it revealed stunned scientists and the public alike. Pluto wasn't a frozen fossil, it was a living world sculpted by chemistry and motion. The images showed a surface that defied expectations. Great ice mountains stretched for kilometers into the sky, built not of rock, but of frozen water as hard as granite. Nitrogen glaciers flowed like rivers across wide plains, reshaping the landscape. But the biggest surprise hovered above the surface. Pluto had an atmosphere. It wasn't thick, but it reached more than 300 kilometers high, layered like gauze. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this fragile envelope scattered sunlight into a soft blue glow. The haze forming that glow fascinated scientists. Its origin lay in chemistry driven by sunlight, though sunlight on Pluto is 1,000 times weaker than on Earth. Even so, ultraviolet radiation from the sun has enough energy to split methane molecules in Pluto's upper atmosphere. When this happens, the fragments, methyl radicals and hydrogen atoms, begin to recombine, forming more complex hydrocarbons like ethane, ethylene, and acetylene. These molecules continue to link together, step by step, into even larger compounds. Eventually, they form solid, carbon-rich particles known as tholins, a kind of reddish organic dust. As these tiny grains drift downward, they collect in distinct translucent layers that give Pluto's sky its ethereal blue color. Unlike Earth's haze, which comes from moisture or dust near the ground, Pluto's haze is born high above its surface through ultraviolet chemistry.
It's more akin to the atmosphere of Titan, Saturn's largest moon, where similar reactions produce a smog of orange organic particles. But on Pluto, this haze turned out to be more than just decoration. It held the key to understanding why the dwarf planet's atmosphere was so cold. Before New Horizons, scientists thought they understood Pluto's climate. Its thin atmosphere, dominated by nitrogen, should absorb sunlight and trap enough warmth to maintain predictable temperatures. But the probe's measurements shattered those expectations. Instead of being around 100 Kelvin, Pluto's upper atmosphere hovered between 65 and 70 Kelvin, colder by more than 30 degrees. For a planetary scientist, that discrepancy was enormous. It meant something was cooling Pluto's atmosphere more effectively than any known process could explain. Years of modeling failed to solve the riddle. Then Shi Zhang, a planetary scientist at the University of California, Santa Cruz, proposed a daring solution. What if Pluto's haze wasn't just a passive mist floating in the air? What if it was active, absorbing sunlight and then re-radiating that energy away as infrared heat? On Earth, the main factors controlling atmospheric temperature are gases: carbon dioxide, methane, water vapor. Solid particles like dust or haze usually play only a minor role. But on Pluto, Zhang suggested things might be different. The haze particles could dominate the planet's thermal balance, cooling the atmosphere by re-emitting absorbed energy as mid-infrared radiation into space. The idea was radical. No one had ever observed a planetary atmosphere controlled primarily by solid particles rather than gases. But testing the theory was nearly impossible. Pluto is tiny, distant, and faint. Even the best telescopes on Earth could barely separate it from its large moon, Charon. Measuring the faint mid-infrared glow from individual haze particles was far beyond existing technology. The evidence would have to wait. Then came the James Webb Space Telescope. Launched in 2021, Webb was designed to peer into the coldest, darkest corners of the cosmos with a massive mirror and instruments sensitive to infrared light. Among them was the Mid-Infrared Instrument, or MIRI, capable of detecting radiation in the 5 to 27 micron range, the very wavelengths that Pluto's haze would emit if Zhang's theory were correct. In May 2023, an international team led by Tanguy Bertrand finally put that prediction to the test. For the first time, scientists were able to clearly distinguish Pluto and Charon in infrared light. Earlier observations had always blurred the two worlds together, but Webb's unprecedented resolution changed that. The team gathered detailed thermal data using MIRI, carefully modeling how much infrared heat came from each body. By comparing Pluto's emissions at different wavelengths and subtracting Charon's contribution, they isolated the faint signal from Pluto's atmosphere itself.
The results were astonishing. The infrared glow from Pluto was stronger than could be explained by surface ice alone. Something above the surface was radiating additional heat, exactly the behavior Zhang's model predicted. When the team compared their data to simulations that included haze particle emission, the match was almost perfect. Pluto's haze was indeed glowing in infrared light, cooling the atmosphere by radiating energy into space. This discovery marked a turning point in planetary science. For decades, researchers had assumed that gases were the dominant regulators of planetary temperature. On Earth, greenhouse gases trap heat. On Mars and Venus, thin or thick atmospheres determine how energy circulates. But Pluto demonstrated something new, a world where tiny solid haze particles, not gases, control the entire climate system. Under the right conditions, haze can dominate atmospheric physics. Webb's observations didn't stop there. With its fine-tuned infrared vision, the telescope also provided new insights into Pluto's relationship with Charon. Scientists found evidence that Pluto's methane-rich atmosphere is gradually leaking into space. Some of this methane drifts outward and eventually settles on Charon's poles. There, under the influence of sunlight and cosmic rays, the methane molecules transform into reddish organic compounds, the very material that stains Charon's polar caps, first glimpsed by New Horizons. Webb confirmed that this strange color isn't just a surface stain, but a chemical imprint of Pluto's lost atmosphere, frozen in place on its moon. Beyond solving Pluto's cooling mystery,
Webb's findings have profound implications for other worlds. Titan, Triton, and several distant icy bodies in the solar system also have nitrogen-based atmospheres thick with haze. Until now, scientists believed that gases alone explained their temperature patterns. But if haze dominates Pluto's climate, it might play a similar role elsewhere. This discovery could force researchers to revisit long-standing models of atmospheric chemistry and energy balance across the outer solar system. The implications extend even further, to worlds far beyond our own solar system, orbiting stars light years away. Over the past 2 decades, astronomers have discovered thousands of exoplanets, each presenting its own enigma. Many of these distant worlds are wrapped in thick, hazy atmospheres that obscure their surfaces and distort the starlight passing through them. From super-Earths to mini-Neptunes, their skies are often filled with suspended particles, microscopic grains of hydrocarbons and ices that scatter light and complicate efforts to measure their true composition. When telescopes such as Hubble or Webb observe these exoplanets, the haze acts like a cosmic filter, muting the chemical signatures scientists rely on to understand what those atmospheres are made of. For years, researchers modeled these alien environments using the same assumptions that describe Earth, Mars, or Venus, worlds where gases dominate climate and energy flow. But Pluto's strange behavior suggests that this approach may be incomplete. If haze can dramatically influence temperature and radiation balance, then many of our existing models could be missing a crucial piece of the puzzle. The thermal structures, weather systems, and even potential habitability of exoplanets might hinge on the microscopic behavior of suspended particles rather than on the gases alone. In extreme cases, haze could act like an atmospheric thermostat, reflecting sunlight to cool a planet or trapping heat to warm it, depending on its composition and altitude.
This means that planets once dismissed as too cold or too hot for life might, under the right hazy conditions, exist in far more temperate states than previously believed. A thick hydrocarbon haze could protect a planet from the full glare of its star, creating a stable, cooler surface environment, while another type of haze could help retain heat in a world otherwise too distant to remain warm. Some exoplanets orbiting dim red dwarfs or bright volatile suns might owe their very stability to such delicate atmospheric filters. If haze plays as active a role elsewhere as it does on Pluto, then our search for habitable worlds, and perhaps for life itself, will have to expand to include this new dimension of climate physics. Perhaps most intriguingly, Pluto's story may echo our own planet's ancient past. Around 2.4 billion years ago, before the Great Oxygenation Event transformed Earth's skies, our atmosphere was likely dominated by nitrogen and methane. Bathed in ultraviolet radiation from the young sun, those gases produced a global haze, much like the one enveloping Pluto today. That prehistoric veil of organic particles could have moderated Earth's climate, shielding the surface from harmful radiation while helping retain the warmth necessary for liquid water and early biochemistry. Some scientists even suggest that the chemistry within that haze may have contributed to the formation of complex molecules, setting the stage for the first living systems. In this way, Pluto becomes not merely an icy curiosity at the edge of the solar system, but a time capsule, a glimpse into the atmospheric chemistry that might once have governed our own world. By studying how haze cools Pluto's skies and shapes its environment, scientists gain a model for understanding how similar processes could have stabilized early Earth and how they might be operating today on countless exoplanets orbiting distant suns. From that frigid outpost beyond Neptune, Pluto has compelled us to rethink the rules of planetary science. What began as a puzzling temperature anomaly evolved into a revelation about the hidden power of haze, the subtle dynamics of atmospheres, and the interconnectedness of worlds across space and time. The James Webb Space Telescope, with its unmatched infrared vision, did more than confirm a bold hypothesis. It opened a new window on how planets work, how climates evolve, and how the smallest particles can shape the fate of entire worlds. Pluto, once dismissed as an icy leftover, has proven itself to be a laboratory of cosmic physics, a reminder that even the smallest and most remote bodies can hold the biggest surprises. In the dim light of the outer solar system, it continues to rewrite what we think we know, not only about itself, but about the very nature of worlds across the universe.